Welcome to the short video on Hadley cells and their effect on global wind circulation patterns and also on global climate. Before we talk about wind and air movement across the globe, we first need to review a little bit why rainfall happens. So here we have a kind of a flat landscape, and remember that close to the Earth's surface, temperatures are relatively warm. But as we move up through the atmosphere, temperatures cool down and get colder and colder. Okay, so with that in mind, let's take a look at an air mass close to the Earth's surface. This air mass contains water vapor. And remember that water vapor is just water in a gaseous form. So there's no raindrops here, there's no cloud, it's just an air mass with water vapor contained within it. Now, if we take that air mass and move it up through the atmosphere, it starts to cool down. And as it cools down, that water vapor begins to condense to form water droplets. And those water droplets form clouds. If we keep taking this air mass and pushing it up into the atmosphere, the cloud gets bigger, but also the water droplets within the cloud get bigger. And it's at this point that rain can develop, because the water droplets are now heavy enough to begin falling down as rain. So the key process here in creating rain is to take an air mass with water vapor in it and push it up into the atmosphere at higher levels so that it cools down and that water vapor condenses to create water droplets and eventually raindrops that are big enough to fall down to the Earth's surface. Now, there are a number of ways of pushing air masses up into the atmosphere. Let's take a look at one of them. So here we have a mountain range over to the right, and let's start with our air mass over here close to the Earth's surface. And again, this air mass contains water vapor. And let's take some wind and push that air mass up a mountain. So as that air mass begins to cool, clouds begin to form, because now that water vapor is condensing into liquid water. And if we keep pushing this air mass up this mountain, water droplets get big enough to create rain. So just like what we saw before, we're taking an air mass with water vapor in it, we're pushing it up higher into the atmosphere where it's cooling down, and that water vapor then is condensing to form water droplets, and when those water droplets get big enough, they fall down as rain. Now you might be asking yourself, well, what happens if we take this air mass and instead of pushing it up into the atmosphere, we push it down? And what happens is just the opposite of what happened when you're pushing it up. The rain, the liquid water turns back into water vapor. So essentially the rain within that cloud evaporates. and you don't get any rainfall over on this side of the mountain. And so this area, this is a very common phenomenon with mountain ranges. This area is called a rain shadow because air masses are descending in elevation, and as a result, they're warming up, and the liquid water within the air mass evaporates, and you lose those raindrops and that liquid water. We can see a really good example of that in California. So just to get you situated, down here we have San Jose. Some of you might recognize this big lake. This, of course, is Lake Tahoe. And just west of Lake Tahoe, we have the Sierra Nevada range. Now in California, air masses come off the Pacific Ocean and go eastward. And when they hit the Sierra Nevada, those air masses get pushed up into the atmosphere, they cool down, the water vapor condenses to form raindrops, and as a result, a lot of rain falls on this side of the Sierra Nevada. And we can tell because you can see all the vegetation growing on the western slope of the Sierra Nevada. It looks very green. Now, when these air masses move up over the Sierra Nevada and descend back towards Nevada, you can see that these air masses are much drier. And this has the result of creating essentially very dry conditions back here, and you can see that there's just very little vegetation growing in Nevada. So this whole area then is the rain shadow. Okay, so air masses get pushed up the Sierra Nevada range, you get a lot of rainfall, and then when those air masses descend back down towards Nevada, those air masses essentially dry up, the water, the liquid water turns into water vapor, and there's no rain back here in this rain shadow. Okay, so with that in mind, let's take a look at Hadley cells. So here we have the Earth. This line is the equator. So that's 0 degrees latitude. And then, of course, over here, this is the sun. Now, because the sun more or less rotates around the equator, the sun's rays are much more intense at the equator. So we have intense solar radiation. When the sun's rays hit the higher latitudes, however, they're spread out over a larger region, and so the solar radiation isn't as intense. And this explains then why the equator is very hot, and why at the poles, so for example here the North Pole, it's relatively cold. And it just has to do with the fact that the sun, I said the sun rotates around the equator, but of course it's the Earth rotating around the sun. But the sun is more aligned with the equator, and as a result, the temperatures are hotter at the equator than up at the poles. Now, let's take a look at what that does with respect to the air patterns. So we know that when things warm up, they become more buoyant, they become less dense, and they tend to rise. So if you look at air right around the equator, it rises up. And it's just the opposite here at the poles. The air is cold, and as a result, the air subsides, it goes down. And so under ideal circumstances, this would set up a big circulation cell where air would rise up at the equator, flow towards the poles, descend at the poles, and then move back towards the equator along the surface. Okay, so we see a big circulation cell here with air rising at the equator, traveling up at the highest levels of the atmosphere, reaching the poles, cooling down, descending, and then moving back along the surface towards the equator. Now, like I said, this is what would happen under ideal conditions, but there's another complication here, which is that the Earth rotates. As a result of this rotation, this big cell gets broken up into 3 smaller cells. So we have one cell. Again, we have air rising up at the equator like this. But then the air starts to descend. And so we get a smaller cell right there. And this happens at about 30 degrees latitude. And remember, the equator is 0 degrees. Now there's another cell that develops between 30 and 60 degrees latitude. Where the air follows this kind of path. And then another cell between 60 and 90 degrees. Where the air follows that path. Now I'm going to draw, so this is all in the northern hemisphere. I'm going to draw just one of these cells in the southern hemisphere, and you'll see why in just a second. These smaller circulation cells are called Hadley cells. And as we'll see in just a second, they're responsible for some of the major patterns that we see on our planet with respect to climate. Now let's take a look at what's happening here in the equator. We can see that the air is rising, and so what that means then is that water vapor is consistently being turned into liquid water right along the equator, and so you'd expect to see a lot of precipitation, and in fact, that's exactly what we observe. Down here we have the Amazon basin. This is South America. This is right along the equator, and you can see there's a lot of green, there's a lot of big rivers, and this is all a consequence of this rising air between these 2 Hadley cells that creates a lot of precipitation. Now, if we move up to 30 degrees, we see a different situation. We see a lot of air being pushed down. And so this is just like what we saw with the example with the mountain range, where you have air being pushed down, it warms up and it dries the air out. So it converts that water, the liquid water, into water vapor, which doesn't give any precipitation. And so, whereas around the equator, you get a lot of rain, right here at around 30 degrees, you get a lot of dry air, which results in deserts. Here's a picture of the west coast of North America. So we can see Baja California right here, and then Los Angeles is right around here. And so this is all around 30 degrees latitude, and notice how dry it is. And in fact, we see this around the globe where all the areas around 30 degrees latitude tend to have deserts. Now let's move up to the next set of Hadley cells, and right around 60 degrees latitude, we see air rising again. And so you'd expect a lot of rain right at around 60 degrees latitude. And in fact, that's what we see. So this is up in Canada, right around 60 degrees latitude. Alaska is right there, just to get you oriented. And you can see a lot of lakes, a lot of vegetation. And so this is telling us that there's a lot of rain through this area. Okay, thank you for your attention. I hope that was useful.